All right, so this electrostatics question I think is a really good representation of whether you sort of understand what we've talked about when we talk about electric potential energy without doing a whole lot of calculations for it. So it's a really, really important one to be comfortable with in practice. And so if this one doesn't make sense to you, this is a big area to review, I would say. All right, so we're given a picture, essentially, of two charged objects, charged spheres, X and Y, that are fixed exactly where they're placed. And around those two spheres are isolines of electric potential. And so the first thing, to even begin understanding this question, you have to understand what that phrase means, isoline of electric potential. And I'm pretty sure I've used that phrase, but maybe not as much as I should have. So an isoline means a constant line. So each of those lines are lines of constant electric potential. So, for example, where point A is, if you know the potential at point A, you know the potential at every point on the line that point A is on. At point B, that circle that it makes, if you know the potential at point B, you know the potential of every single point on that circle, and so on. That's what the isoline of electric potential means, a line of constant electric potential. And we're also told that each of those constant potential lines differs from the line that's next to it by 10 volts. We don't know yet whether it increases on the way out or on the way in, but we know that the difference between, say, points A and B must be 20 volts, because there's one line in between. So B to the middle line, and then the middle line to A, 10 volts, or a total of 20 volts. And we're told one more thing, which is the outermost line is sitting at a 50-volt potential. Actually, one other thing that's important is that we're told sphere Y is positive. We don't know sphere X is charged, but we know sphere Y is positive. So, part A, indicate the values of the potentials, including the signs, at points A and B. So we know the outer circle is 50 volts. So that means point A is either 40 or 60, right? A 10-volt difference. So it's either 40 or 60. You have to put one of those two. If you put anything else, then you didn't read the problem very well, or you don't know what isoline means. But it's got to be 40 or 60. And we know that Y is positive. And the last thing we know from our definitions and conventions is that the electric potential increases the closer to positive charges that you get. So as we move from the outer line to point A, we're getting closer to sphere Y, so the potential must increase. So that means it must be 10 volts larger, and so point A is 60 volts. And if you wrote a positive sign, that's probably a good idea, but you would get credit if you just wrote 60, as long as you don't have a negative sign anywhere. So that's what point A is. And with that same reasoning, point B is pretty easy. If point A is positive 60 volts, then the line that's in between A and B must be 70, and then another line in, again closer to sphere Y, must be 80 volts. And once again, you could write the positive or not. It's not asking you to explain, but you have to be able to reason through what I said to get it right. That being said, if you're sort of unsure whether the potential increases or decreases, you're either going to put 60 and 80, just by the definition of each line being 10-volt difference, or you're going to put 40 and 20. Anything else, I think, is a larger misunderstanding. Okay, so part B1, 2 pieces, plus an explanation. So the first thing to note is that the electric potential, right, is given by that equation, right? We know that. So for the spacing between equal potential lines to be very close together, right? So that would be like a large delta V for a small r. That requires Q to be bigger, right? So because the equal potential lines are closer together for sphere X than they are for sphere Y, charge X must be bigger than charge Y. That's one way to get at it. The other way, same sort of reasoning, is we recognize that if we sort of follow the circle of what is between point A and B, so that's the 70-volt line. That 70-volt line is way closer to point X than it is to point Y. And so if we have 70 volts equals KQX over small r, and 70 equals KQY over large r, right? If for this to be true, right, this ratio has to be a constant, right? And so what this ends up showing us is that since the 70-volt point is closer to X, X must be the bigger charge for that to happen, right? So either of the explanations works. I like the spacing of potential lines. I think that's easier to recognize. That's like this one. But either one would work. So that gets us the magnitudes, is X. So I'll write that QX must be greater than QY. How do the signs compare? Well, there's two different ways you can approach this one as well. The first is that electric potential is not a vector. And so if charges X and Y are of opposite signs, there must be a point somewhere in between them that's zero potential. And there is no such point, right? The circles keep getting bigger and bigger and bigger as you move in, as that's what we did in part A. So since there's no zero potential point in between them, they can't be the opposite sign, right? So they must both be positive. The other way is to remember the relationship between equal potential lines and field lines, right? The field, the direction that a positive charge would move, is perpendicular to the equal potential lines. As you sketch some of those, you will find that a positive charge will have to move away from both of them. And that means that both charges Q and charges X and Y must both be positive because they both repel a positive charge. Either way would work. Okay, so part C. Part C is something that really forces you to think back to Physics 1. Or actually, I forgot part 2. Oops. Yeah, B part 2, which is going to be related to part C, which is why I jumped. So B part 2 is relating gravity and this electric stuff that we've done. So we're told that spheres X and Y have masses that are sort of similar to their charges. And as a result, the gravitational isolines have similar shapes. And the question is why? Well, let's think about what we know about gravitational potential energy. UG is negative G M1 M2 over R. And we know what the electric potential energy is, right? And these look very similar, right? One has a product of two masses, the other has a product of two charges. They both are 1 over R dependence. They both have a constant that tells you sort of the strength of the force in front. So if we know what writing the electric potential is, right, that's like KQ over R. So you can write a sort of gravitational potential, which is going to be negative GM over R. And so why do they look similar? Well, the equations are very similar, right? Because the gravitational force is very much like the Coulomb's law force, the gravitational potential energy and the electric potential energies are similar, and therefore the gravitational potential and the electric potential must be similar. I don't know of any other way to really explain it other than that. You have to remember sort of this relationship, right? These are on your AP sheet. And if you see that those are similar, that tells you why the potential lines, the iso potential lines, are similar. Now we're on to part C. And so we've discussed a little bit about why they're similar, and we need to describe in a bit more detail one very specific similarity and one very specific difference. And I don't know of any differences that would generally apply to all forces, but things like similarities, well, you couldn't say something like, well, they both cause things to accelerate. That applies to all forces. That's general. That's not a fair similarity. You need something that's similar between the electric and gravitational forces that's really only similar between those two, not just any force I name. So there's a couple different things you could put there for similarities, but the easiest thing I can think of is just going straight to the equation, right? The gravitational force and the electric force, right? If these are your equations, there are some very obvious similarities, right? First one, they're both inverse squares, right? That's probably your best bet, I think. You could try to do something that says like this a product of the masses and a product of the charges, but that's kind of more of a difference. But the idea is like a product of both interacting objects. You could maybe do that, but I think the inverse square law is the best. Differences. Well, one big difference is this constant, right? That tells you the relative strengths of the forces. And so the fact that G and K are such different values tells you the electric force is almost always, well, the electric force is a stronger force than the gravitational force. So their forces are going to be different magnitude, even though they sort of behave similarly. Another thing, the electric force is going to repel, right? These are positive charges. If we put a proton nearby, the proton is going to be repelled by the electric force, but it'll be attracted by the gravitational force. So that'd be another difference. All right, so part D now. So we need to determine the change in electric potential energy, and we need to express the answer symbolically. So the first thing to note is if we put a proton at point B and charges X and Y are both positive, it's going to move away. Specifically, it's going to move towards point A. So moving through a potential difference of 20 volts means that it's now on the iso line associated with point A, because it's moved away. And so delta U E is Q delta V, right? That's the definition of potential. Q, and we started off at potential of B. We ended up at the potential of A, right? And so that's your answer, right? That right there. Again, if you messed stuff up earlier and you concluded that it would move from B to C, then you might get that flipped that way, but that's why, right, that symbolically uses what we're given. So that's part one. Part two, now we're going to do the same sort of calculation, but in terms of work. So the electric force is always perpendicular to the direction of motion. We know the definition of work is force times distance, and it's basically an average force. And we know the relationship between the electric force and electric field is Q E average times D. And that's it right there. That's the whole thing. Right? This is a part that sort of, if we were in physics C-level class, you'd be doing some calculus in here because, right, this is dealing with an average electric field that changes as over a distance, so it should be an integral. But all you're trying to do is sort of recognize the relationship between the force and the field, that's that Q times E equals F, and the relationship between work and force, the force times the distance. So that's part 2. So part 3 is we have 2 students, and basically each student thought about how to do this question in a different way. Student 1 took the D part 1 approach. So he wants to explain why the kinetic energy of the proton changes, and he says that, well, the system loses potential energy, right? That's this right here. The system loses that potential energy. Therefore, the energy has to go somewhere. It must go to kinetic energy. So the proton gains kinetic energy. Student 2 says that, well, the other stuff's not moving. I don't care about its energy. So the proton starts off at rest and feels an external force, right, the electric field. And that does work. That's this statement right here. And so since work is done on it, it gains potential energy, or it gains kinetic energy. And discuss each student's claims. Well, I kind of already discussed. I expanded a bit more on what they were saying. So there's some answers in part of what I said. But explain why each is correct or incorrect. And the answer is they're both right. They're both right, but because they're addressing different systems. Student 1 includes everything that's involved, and so all the forces are internal, so they talk about changes in potential energies rather than external forces and work. That's a totally fine way to do it, and as we did in part A, you can calculate that change in potential energy, so you can calculate the change in kinetic energy. Student B is still right. If you knew that average electric field, you could talk about the total work done by the external force of the charges X and Y now. And that would be completely correct to say that because of that external force, energy is added to the proton, specifically that Q times E average times D amount of energy, and therefore it gains kinetic energy. The key is to reference sort of the difference between internal and external forces, and if you do that and conclude they're both right, then you're probably going to get it.